Today we will be moving into one of the most important sections of cloud infrastructure, cloud architectures that make services reliable, scalable, and resilient. So let's start today's class with learning about hypervisor clustering architecture. So let's start with what a hypervisor is. It's the software that lets us run multiple virtual machines on one physical server. Now, a cluster means we connect multiple hypervisors together so they behave like one system. When we do this, we get something powerful. If one physical host goes down, another one in the cluster picks up the load. That's how we achieve fault tolerance. Now you'll often hear the term live migration. That means we can move a running virtual machine from one host to another without shutting it down. Imagine shifting a running car from one road to another mid drive and the driver doesn't even notice. All this is controlled from a central dashboard that constantly checks the health of each hypervisor using heartbeats. Small status signals sent every few seconds. If one host stops responding, the other takes over automatically. You'll see this design in VMware, vSphere, Microsoft Hyper-V, and KVM clusters, all aiming for the same thing, keeping virtual servers running even when hardware fails. Virtual service clustering architecture. This one extends the idea into applications inside the virtual machines. We put multiple virtual servers together and make them act like one logical service. Say we have a website. Instead of one server handling all users, we create a cluster of identical web servers. If one crashes, other keeps responding. That's called a failover. This pattern is everywhere in e-commerce websites, banking systems, database replicas. In front of them sits a load balancer that divides user requests evenly. The user sees one address, but behind the scenes, many servers are cooperating to deliver one experience. That's the core idea, teamwork among servers to stay fast and resilient. Here we focus on balancing traffic between servers. Each instance runs the same app, built from the same image, so they are interchangeable. A load balancer watches incoming requests and decides who handles what. It may use rules like least busy server or round robin. When traffic spikes, let's say on Black Friday, the system automatically adds more instances. That's auto scaling. When the spike ends, it shrinks back. Because each instance is stateless, meaning it doesn't depend on local files or memory, we can safely remove or add them anytime. Typical tools like AWS Elastic Load Balancer, Azure Load Balancer, or open source Nginx and HAProxy. Non-disruptive service relocation architecture. Now imagine needing to patch or update a server, but you can't afford downtime. That's where non-disruptive relocation comes in. We cannot move running services from one machine to another while users stay connected. That's possible because of virtualization and shared storage, where the data sits on a network attached volume accessible from multiple hosts. We first train the old server, stop new connections, finish the existing ones, then shift the workload to another node so that the app never stops. Techniques like live migration or checkpoint make it work. Checkpointing means saving the program state so it can resume elsewhere if needed. Industries like healthcare or banking depend on this. They can't tolerate even a few seconds of outage. Zero downtime architecture. Zero downtime means literally what it says. No outages. Everything keeps running. Updates, maintenance, and even failures happen invisibly. We do that with redundancy at every level. Two power supplies, two network paths, multiple data centers. If one fails, the another one keeps going. Updates are done in a rolling fashion. Upgrade a few servers, test, then continue. We isolate faults so one bad node doesn't take the entire network down. Strong monitoring and automation are essential. Systems watch metrics like latency and errors. If something breaks, automated scripts react instantly. This design is what powers 24/7 SaaS platforms like Google Workspace or AWS. Users never see the chaos underneath. Cloud balancing architecture. Cloud balancing spreads workloads across regions, not just servers. If one region is overloaded or offline, the traffic shifts to another automatically. Think of it like an air traffic control for your cloud services. This uses global servers or DNS based routing. They check which region is closest and healthiest, then sends the users there. That's how Netflix streams from the nearest data center to you. If an entire region fails, say due to a natural disaster, traffic reroutes instantly. That's called geo-redundancy. It is common in multi-cloud setups where a company runs in AWS and Azure simultaneously to avoid a single provider risk. Resilient data recovery architecture. Let's talk about disasters like floods, power failures, ransomware, things that completely knock out data centers. A disaster recovery plan ensures the service can come back quickly. Data is constantly replicated to a secondary site, sometimes in real time, that is synchronous, sometimes with few minutes delay, asynchronous. If the primary site fails, automated failover starts. The backup site becomes active, DNS switches over, apps restart, and users connect there. Every organization defines RTO, how long the recovery can take, and RPO, how much data loss is acceptable. You don't want the first real disaster to be your first practice. So teams run disaster recovery tests regularly, simulate failures, verify if recovery works or not. Now, for data sovereignty, meaning data must stay under the laws of the country where it's stored. For example, GDPR in Europe says personal data can't be moved outside the Europe without safeguards. HIPAA governs how US healthcare data is handled. Cloud providers solve this with region log storage. When you choose US East or Europe West, it physically stays in that jurisdiction. Everything is encrypted, both at rest, which is stored on a disk, or in transit across networks. Access is tightly controlled through keys and managed by a key management service. Auditors check logs to provide compliance. That's called an attestation. For global companies, this isn't optional, that's the law. Resource reservation architecture. This architecture guarantees critical apps always have enough resources CPU, memory, bandwidth. In shared environments like the cloud, one noisy neighbor can hog everything. To prevent that, we reserve or reallocate a slice of capacity for certain workloads. You'll see this in service level agreements promising a fixed performance. For example, a finance app may reserve 64 CPUs and 1 terabyte of storage every night for reports. In Kubernetes, we call these requests and limits. In AWS, reserved instances lock capacity for steady workloads. This is how we keep performance predictable when multiple tenants share the same infrastructure. Dynamic failure detection and recovery architecture. Failures happen. The key is catching them fast. Health checks runs every few seconds. They ping servers and expect a simple I'm alive response. That's their heartbeat, like we discussed before. If a node stops answering, the system automatically restarts it or replaces it. That's self healing. Orchestrations like Kubernetes or AWS autoscaling groups do this constantly. They remove unhealthy instances from load balancer and launch new nodes. This design means user might never notice a crash. It's detected, replaced, and healed before it becomes visible. Rapid provisioning architecture. Provisioning here means setting up new infrastructure. Infrastructures like servers, storage, and networks. Rapid provisioning just automates the whole process. Instead of clicking through a console, we use templates and infrastructure as code tools like Terraform or CloudFormation. We define everything in code, what instance type, what network, what firewall rules, then launch it in seconds. This allows elastic scaling. When demand increases, new machines appear automatically and disappear when traffic drops. It's how modern cloud systems handle massive surges instantly without manual work. Storage workload management architecture. Here we deal with how data moves in and out of storage efficiently. Different workloads have different needs. Databases want low latency, analytics want throughput, so we used tier storage, fast SSDs for hot data, cheaper disk, or cloud object storage for archives. The system monitors input output operations and balances traffic to avoid slowdowns. We enforce quality of service rules so one workload can't flood the disk. Caching and replication also plays a role. We keep frequently used data closer to where it is needed. The goal is steady, predictable storage performance even during heavy activity. Virtual Private Cloud Architecture or VPC. A VPC is your own private section of public cloud, isolated from everyone else. Inside it, you find your own IP ranges and split them into subnets, some public and some private. Public ones host load balancers, private ones hold the databases or internal apps. You secure them by using firewalls, security groups, and networks ACL. ACL stands for Access Control List, which are basically rules of tables saying allow this traffic and block that. If you need to connect your company's network, we use a VPN or a private direct connect link. You also control routing using route tables and NAT gateways, so private systems can reach the internet safely without being exposed. The end result is secure multi-tier cloud network that behaves like your own on-prem data center but with cloud flexibility. And that is all for today's class. I'll see you again on Monday.